Alright, section 4.2 is going to be talking about friction. By the end of today, I will be able to recognize and calculate something called static and kinetic friction, also referred to as dynamic friction. So one is a stationary friction, one is going to be a moving friction. So let's just take a second and talk about what factors might affect the amount of friction experienced by an object. So take a second, maybe just pause and think about that. Okay, so you've had a chance to think about it. So the ones that normally come up are surface area, and that could also be the shape of an object. So something like a rake with its really pointy pointy ends of a rake have small surface area, so they're going to grip a lot more. You'll have a higher friction coefficient or friction effect. Types of material, so rubber versus Teflon versus smooth plastic, all of those types of things will slide differently. And then the mass of the object. So this is partly inertia, but also the larger a mass of an object, the more friction it will generate with the surface underneath it. So if you ever tried to push or pull a heavy object across any significant distance, it always seems to be the most difficult at the start, but once the object is moving, it gets easier to move the object. A snowman is a classic example of this. As you get that snow person larger and larger, if you let it stop moving, it becomes really difficult to move, but once it's rolling, it doesn't seem to be too bad. So we'll talk a little bit about why that is. I've got a short little video here to show you to talk about that.
Alright, this is a very simple friction demonstration. I've got a metal baking pan on a wood surface with a Newton spring scale here. There's a 1 kilogram mass and the tin pan is about 320 grams. So now what we should see, we'll come right down here to the spring scale. Try to get it hooked up again. Okay, is that I can actually pull on the spring scale, and I'll get it in right in close. Okay, and you can see I'm pulling with almost, oh, there it moved. See that? So I was pulling with almost 2.6, 2.8 newtons. Okay, and I got up to 3, and then it moves. Okay, so that's overcoming something we call static friction. I'll just back it up, I'll do it again, and I'm going to keep pulling this one. So after we pull it, okay, so it's going to increase, and then it will slip. Okay, and then we should see that it slips back to a smaller value. So I got up to about 2.8. I'll let it stop again. There's, 3.2, and now I'm pulling it at a constant rate, and it drops back down to about 2. Okay, I'll do that one more time. So the amount to get it to slip, okay, let's see, we'll get to about, there's 3, and pulling at a constant 2. Okay, so for that apparatus, there was a static friction force of 3 newtons I had to overcome, and a 2 newton kinetic friction force as I kept pulling it. So I did that experiment with a couple of different masses, just kept adding them to the trays. Different parts of the table reacted a little bit differently. So I did do some raw data, but then I organized it again a little bit better for reading purposes. So a couple of things should stand out for you. As the mass increased, the F of G increased, which means my normal force increased. And what you should see is that all of the forces for friction increased with that increase in mass. Now here's what's really interesting, and we're going to talk about this more in a minute. If I take the ratio of the normal force and the static friction force, okay, and I put the friction force over top of the normal force, you'll notice I get the same ratio values every single time. So if I put 1.4 over 8, okay, you do the division, you're going to get 0.17. The kinetic ratio, again, look at, there's the exact same numbers, okay, by taking 1.2 and putting it over top of 8, so dividing 1.2 by 8, I get about 0.15. And what's really fascinating is that you can keep adding masses and keep increasing this normal force, and the frictional force will grow with this type of relationship. Okay, so you'll also notice that static is slightly larger than kinetic. That's to be expected, and we'll talk a little bit about that in a minute. So lots of interesting things. You could even try this at home. Could find a different way to measure forces. It's a pretty easy lab to try, And yeah, it's kind of neat.
Okay, welcome back. So hopefully you got to see static friction in action. So that's the force exerted on a stationary object by a surface that prevents the object from starting to move. Okay, so just something stationary on your dashboard of your car stays there because of static friction. Okay. The other is kinetic friction. This is the force exerted on a moving object by a surface and acts opposite to the direction of motion of the object. Okay, the fact that you can walk across the floor is a result of kinetic friction. Okay, so that is as your shoes grab the ground, you will be able to actually move across the floor. If they didn't grab the ground, then you would be standing in one spot for the rest of your life. Now, one of the interesting pieces to this is they're not the same value all the time. So the force generated by each one of these frictions is a little bit different. So you can see something here called Fs max. Okay, and this is the maximum amount of static friction before something will slip or slide. And then kinetic friction's lower, and you saw that hopefully in the videos. You saw that once it starts to move, okay, the amount of friction is different for a static object versus a moving object. So we have something called the coefficient of friction. Okay, and the coefficient of friction, it's a ratio. Okay, so it's a ratio used to express the degree or level of friction created between an object and the surface it is in contact with. Okay, so it's kind of like a score on how frictionless it is or how sticky the surface is in terms of how the two objects are going to interact together. Okay, so we have something called FF, I just called it that, so force of friction, and we'll see that it could be kinetic or static. FN, that's normal, not net, that's the normal force, okay, which is the contact force. And you have this really strange symbol that looks like a U with long legs. It's called mu, and it's the coefficient value. It's also unitless, so there's no value for mu that has units on it. So if you look here, you have a newtons divided by a newtons, so those would cancel each other out. So mu will be unitless, it'll just be a number. Okay, so this is one way you can see the coefficient expressed. It's the force of friction over the normal force. Or, and this is a slightly different way of approaching it, if you rearrange that equation, you can kind of think of mu as the percent of the normal force that turns into a force of friction. I like that method because it allows me to think a little bit differently when I start to see coefficients of friction. Okay, if you want to put in some of the more traditional subscripts, so you could see there's an S here for static, a K here for kinetic, it could also be a D for dynamic. One thing we should note though is that static friction, okay, so the force generated by static friction will be greater than the force generated by kinetic friction. Okay, so this guy here is usually larger than this guy. Usually, not all the time. The other thing to keep in mind is this idea of slip. So when something slips or it moves, that's when you have overcome the static friction force. Okay, so different materials generate different coefficients of friction. So we've got a couple here. These are right from your textbook. Okay, so if you're into automotive and those types of things, you've got a whole bunch of rubber on concrete, rubber on asphalt, those types of things. You'll notice they're just mostly in kinetic because those are probably going to be tires and things moving. You could see a big difference between wet and dry. That's a really big difference. And then steel, if you're again working on automobiles or vehicles of some kind, steel on steel, you're looking at 0.78 steel on steel with grease. And this is why we lubricate things with oil and grease. Look at the change. You went from almost 78% to almost 5 to 11%. That's a huge difference. Okay, so that's why we have to put oil and things like that into our car to keep the engine running smoothly. Otherwise, we get a lot of friction forces built up, which turns into a lot of heat and can cause us some real problems. All right, so let's try a problem. A 3-kilogram block of wood sits on a horizontal wooden floor. The largest horizontal force that can be applied to the block before it starts moving is 14.7 newtons. So right there. Okay, once the block starts moving, it only takes 8.8 newtons to keep it moving. Okay, so that's really important. So calculate the coefficient of static friction for the block and the floor. So if we draw a quick free body diagram, it's static friction, so I don't have to have lefts and rights. I can have my FG here, and this is a 3 kilogram object, so FG is going to be 3 times 9.8. So 3 times 9.8 is 29.4 newtons. Now there's also a normal force, which is the one I really need. And now because this box isn't jumping up into the air, I know that this is going to balance in a vertical direction, so the normal force is also 29.4 newtons. Now that's important because if I wanted to calculate the coefficient of static friction, I need my normal force. This 14.7 up here, that represents my maximum static friction force. So when I go to calculate this, I'm going to have Fs over Fn. And when I do my coefficient of friction here, I should put a little s in there just to keep track of that. I can put 14.7 newtons on the top, 29.4 newtons on the bottom, and when I divide those together, do that really quickly on my calculator here, I get 0.5. Okay, so my static friction for this case here is 0.5. Determine the force of friction, let's switch to purple. Determine the force of friction acting on the block if a horizontal force of 6.8 newtons acts on the block. Okay, now this is a really important idea because the force of friction here is just going to be 6.8 newtons. Okay, it isn't until you overcome the 14.7 maximum static friction amount, okay, that this thing will move. So any force you apply until it's greater than 14.7, the friction force is just going to balance it. Okay, that's a big idea. Okay, so at 6.8 it's not going to move. The friction force is just going to match whatever your applied force is. Calculate the maximum magnitude of static friction. So we're on part C. Calculate the maximum magnitude of static friction acting on the block if a 2.1 kilogram object is placed on top of it. Okay, so now we're going to take this same picture. Let's get rid of all that. And now we have 3 kilograms, and then we're going to put another box on top of 2.1 kilograms. Okay, so that now has a mass of 5.1 kilograms total. Okay, so now calculate the maximum magnitude of static friction. So what we should see, because the mass is greater, our normal force should go up. So we should expect the force of friction should go up as well, but let's go prove it. So Fg here will be 5.1 times 9.8. So let's just say that's 50 newtons. That means my normal force, because again these boxes aren't moving in the vertical direction, is 50 newtons. Okay, so calculate the maximum magnitude of static friction. So now if we grab our formula here, we know this is related. And we found in part A that our mu static was 0.5. Okay, so I can put in 0.5 for mu. I can put in my static friction, and I can put in my normal force of 50 newtons. If I solve for that, I get 25 newtons is my new SS max, FS max. So my new static friction maximum, because I've increased the mass of the object, it's going to take a larger force to get this moving. Okay, and then lastly, determine the coefficient of kinetic friction. So let's once again, we'll clear this. And I'm going to assume that's just on the first block, so I'm going to say that's just 3 kilograms. And our mg here, get back to here for a minute. So we have Fg is 3 times 9.8, and that was 3 times 9.8, better type that in right, that was 29.4 newtons. Okay, so I know my Fn is again the same thing, 29.4. Okay, But now I'm working with this 8.8. Okay, so my force of friction, I'm going to call it force of friction kinetic, is 8.8 newtons. So if I set up my equation again, only this time I'm working with kinetic. I'll just put a K in there, and there's Fn. Better give myself a little bit more room to write. Okay, so we have mu kinetic equals 8.8 divided by the 29.4. Okay, so 8.8 divided by 29.4, and I get a kinetic mu of more or less 0.3, which is less than the 0.5 static, which shouldn't be a big surprise because we've already talked about that the kinetic coefficient should be less than the static coefficient. Okay, here's a couple problems to try. So if you want to pause this right now and then try a couple of these. Okay, so let's take a quick look. Determine the coefficient of friction of each situation. It takes a horizontal force of 62 newtons to get a 22 kilogram box to just start moving. So right away, that 22 kilograms leads to a 22 times 9.8. So let's say 216 Newton Fg. If it's not moving, my normal should be the same. And then we should end up with 62 over 216. And 0.29 should be our mu for that. And that's what we get. Okay. It only takes 58 newtons of horizontal force to move the same box at a constant velocity. Exact same expression, only instead of the 62 you put in the 58 and you come up with 0.27. Okay. Hockey player, 75 kilogram hockey player glides across the ice on his skates with steel blades. What is the magnitude of the force of friction acting on the skater? So you'd have to go down to this table down here, and let me just clear out some of my information. Okay, so we're going to have to go down and find steel on ice. There it is right there. Okay, and it says he's moving, glides, so we are working with a kinetic of 0.01. Okay, so what is the magnitude of the force of friction? So, and we know it's a 75 kilogram hockey player, so if we do this relatively quickly, we would have mu equals force of kinetic friction, make this a K, and my normal force. So I know this is 0.01. My force of kinetic friction is what we're looking for, and my normal force, again, the hockey player is assumed to not be moving up into the air, so there's no vertical. And then if we multiply those things together, 0.01 times 75 times 9.8, 7.35 should be my kinetic friction. Let's say 7.4 newtons. So let's have a quick look. So there's the 7.4 newtons. And lastly, a 1,300 kilogram car skids across an asphalt road. Use table 1 to calculate the magnitude of the force of friction acting on the car due to the road if it is dry, wet, covered with ice. Okay, so the same sort of system we've been working on. You set up the 1,300 kilogram car, you get the normal force, then you can use the different coefficients of friction to determine what the forces are. And if you do that, you should come up with a range, okay, because there's a range provided. And that's all it is they use the different range of mu values. Okay, so finishing up section 4.2, you can try questions 1, 3, 4, 5, and 9, and thanks for listening.